Hi, everyone. Nice to see you all. And also it's nice to see our today's speaker from University of Lille, who is Nicolas Debarsy, who will today share the results of his joint work about the estimation of the regression model with spillovers. And we proceed as usual. So first the lecture, and then after Nicolas is finished, then you will be able to ask any question or suggest anything or comment somehow. So the floor is yours. And thank you again that you agreed to be with us today.
Thanks, Katerina. So hi, everybody. So thanks a lot for the invitation. I'm really happy to be able to share my research, the research results I have with Vincenzo Verardi and Catherine Vermandelen. So Vincenzo is from Université Catholique de Louvain in Belgium. And basically Catherine is from ULB, so University de Brussels in Belgium too. So just before getting into the presentation, just to let you know that basically what I will present today, it's a mix between two papers, basically. And with Vincenzo and Catherine, we try to follow this research lead of trying to develop efficient estimations, so really precise estimation of the regression model with spillover that you know as the spatial autoregressive models, right? And what I will present you here, it's basically two approaches to efficiently estimate these models. All right. So if I'm not clear at some point, don't hesitate to interrupt me. So that if you have questions, don't hesitate. All right. So basically, linear model with spillovers, which are known as SAR model of spatial autoregressive models, aim at explicitly accounts for interactions or spillovers between cross-sectional units, right? So for instance, in social networks, you're interested in peer effects, or in corporate finance, the influence on the bank on the systems, or in local public policies. Basically, what you will have, a linear model with spillovers, is that one, where you want to explain the behavior of an individual based on its own characteristics, but also based on the outcome of other individuals, which is called the endogenous spatial lag, right? Or in the social network literature, it's called an endogenous effect, all right? This means that the ith outcome depends on outcomes of other individuals, right? And in this model, you can also have what we call contextual effects, meaning that the characteristics of other individuals will affect the outcome of individual I. And to write down this model, what we need to do is to specify an interaction matrix called W or G, depending on the literature, that will model the interactions between observations. And this W can be either based on geography, basically on peers, or socioeconomic indicators, or any relevant space in which your individuals interact. All right? But in this presentation, I will not focus on this W. I will assume that you know the W. All right? We all know that due to this endogenous effect, this WY, basically ordinary least squares cannot generally be used to estimate this model. And basically what we need is we need to have alternative methods, such that two-stage least squares, generalized method of moments, or quasi-maximum likelihood, and I'll put between brackets under normality. I'll come back to that in a moment. Basically, all these models are not equal in terms of efficiency, meaning that some methods, like maximum likelihood, will give you more efficient or more precise estimators than others, such as the two-stage least squares. All right? And more precisely, if the distribution of the innovations of the author is known, like normal distribution, student distributions, whatever, then the maximum likelihood estimators outperforms all other estimators. So this means it will be the most precise estimator. You cannot beat it. All right? However, a drawback of that is that if the distribution is unknown, we don't know exactly what's the distribution of the author, then basically the maximum likelihood is not feasible, and Furthermore, if the distribution you pick, you assume is not correct, for instance, you specify a student distribution, but the true one is a Laplace one, for instance, then basically the estimator, the maximum likelihood estimator, is generally inconsistent, right? So a solution to that has been developed by Longfellow in 2004 in his econometrica paper, where basically it develops a QML, quasi-maximum likelihood estimator, based on the normality, which allows basically for deviation from the normal distributions. So this means that you assume normality of the error term, but even if the error term are not truly normally distributed, the QML estimator will remain consistent. Of course, it won't be efficient because you use a wrong distribution, but nevertheless, it remains consistent. All right? To solve this drawback of the QML, meaning this lack of efficiency, Liu and his co-authors, it's Bollinger and Longfellow, have developed an efficient GMM estimator, so based on moments conditions, which might bring a gain in efficiency compared to this quasi-maximum likelihood estimator. Also, Robinson, in a Journal of Econometrics papers in 2010 also, developed an adaptive estimators, where basically he write down the likelihood function based on some given density functions. And basically what he will do, he will try to approximate the score function using series estimates, right? So that just kind of it can be viewed as a non-parametric estimation. What we do in this presentation, I will basically discuss two alternative efficient estimator, which are both derived from what we call the local asymptotic normality theory that has been introduced by Le Cam in 1960. And more precisely, what I will present you, it's two types of estimator. One is a parametric efficient estimator. So this means that it will give you the efficient estimator, so the most precise one for all parametric distributions. And the other one will be a semi-parametric efficient, where basically what we won't do any parametric constraint on the distribution of the error term. All right? So for the parametric efficient estimator, what we do, we develop an efficient estimator for any parametric distributions as long as the quantile function exists. So the quantile, just in a nutshell, the quantile function is the function that allows you to draw numbers from this distribution. All right? As soon as you can draw numbers from this distribution, the quantile function exists. Okay? And within this parameter efficient estimator, we also propose two flexible distributions, which approximates well many different parametric distributions. All right? So if you want to stay in the parametric world, which can be nice because parametric estimation, if you have the correct distribution, is more efficient than the non-parametric one. Okay, so if you want to stay in the parametric world, what we do here, we propose two flexible distributions. You can have any others, all right? But here what we do, we just propose two flexible distributions which have quite good properties. For the semi-parametric efficient, what we do, basically, as I told you, we don't put any constraint on the distribution of the error term. And the logic behind, I will come back to that, but just to give you the insight about how it works, it's basically, it doesn't use the error term per se in the estimation, but it will use functions of the error terms, more precisely, functions of the residuals, which are independent of the underlying distribution. So what it means is that instead of working with the residuals, we'll work with function of the residuals. And this function will be the ranks and the sign of the residuals. And using only these two functions, we'll be able to find what we call the semi-parametric efficient estimator. This means that we cannot obtain a more precise estimator than the one we have here without imposing more constraint on the distribution. All right? So that's the plan of the presentation here. It's ready to introduce you to these two efficient estimators, one which is parametric, one which is semi-parametric. Right? So how does that work? First, let me introduce you to the local asymptotic normality. Okay, then I will come back on the model. I will explain you the two estimator we propose. Then after that, I will show you how it works in small samples using two different approaches. First, I will rely on Monte Carlo simulations because in that setting, we control for everything. All right, and so that's a practical way of showing that how the estimator performs. And then we will turn to non-empirical illustrations where basically we don't control for anything. All right, and we'll see how the proposed estimators behave on real data. So, what's this LAN property? The LAN, so local asymptotic normality property, basically suggests that under some conditions, which are not really strong, complex model behave similarly to the Gaussian models locally. So basically, in the neighborhood of the true value of the parameters, complex models can be approximated by a Gaussian models. All right, and so this LAN, what it does, it examines the behavior of the model for small changes around the true parameter value. And the key thing about this LAN property, this local asymptotic normality property, is that as the sample size increases, the log likelihood ratio between the true parameter value and its nearby value is normally distributed. I will just show you how it works on the next slide. Importantly, this LAN approach only requires quadratic mean differentiability, which is called QMD, which just means that all you need to have for LAN to hold is that the density function is only differentiable once and not in all points. All right, so you can have a density which is not differentiable everywhere, but as soon as the differentiability occurs in nearly all points, then basically it will work. An example of this of such a density function is the Laplace distribution. The Laplace distribution is not differentiable in zero, right? For the standard Laplace form, just because it's a distribution that way, and so basically the first order condition is not defined in zero. Okay. Nevertheless, it's QMD, so it's differentiable in quadratic mean, and does enjoy the LAN property. So this means that we can estimate a model by LAN under the Laplace distribution, while the parameters cannot be estimated by maximum likelihood, because maximum likelihood requires 2 times or 3 times differentiability of the density functions. So the LAN property, the LAN, demand is much less demanding in terms of assumption. Okay, let's see how it works. Basically, this concept of LAN is well explained in Canay in 2021, that slide course. And suppose, for instance, that you have a normal distribution, P, right? It's a distribution, and we say that it's normally distributed, centered around theta, and with variance sigma square, where we'll say for the moment that sigma square is known. Okay, so the only unknown parameter in your distribution is theta, right? Okay, so as I told you, the LAN consists in writing the likelihood ratio, log likelihood ratio here, in theta, not the true value of the parameter, and in its neighboring value here, where theta is just the neighboring value of theta. Right, tau here is the neighboring value of theta, right? Oops, sorry. And we just scale it by square root of n just to be sure that there's the sample size, you stay in the neighborhood of theta. All right. So if the density, the distribution is the normal is normal, then we write the log of the densities here as this, right? Where here that's the value of the mean in the neighboring value of theta naught minus the density evaluated at theta naught. if you collect terms together, you will get this guy here, okay? And then if you multiply and divide by n, basically you will end up with this guy here, okay? Which we call delta. And delta, basically it's square root of n times the average value minus its true value divided by sigma square, which is normally distributed, centered around 0, just because the sample average is a consistent estimator of the mean of the expected value. All right, and with an information matrix here, I of theta naught, which is equal to 1 over sigma squared. Why is it the case? Just because here we just divided by sigma squared and not by sigma. If we had divided by sigma, then basically delta would be a standard normal distribution. However, as we divided by sigma squared, delta is a normal distribution, but with variance is equal to 1 over sigma squared. Okay? And you can see that basically this 1 over sigma squared appear here. Okay? So basically the log likelihood ratio is equal to a constant, a factor, times delta minus 1 over 2 times tau squared times this information matrix, right? So this means that the log of the likelihood ratio is normally distributed with an average value, expected value, which is equal minus half its variance. All right? That's what happens when you have normal model. Now, what's important to see is that, okay, but what happens if the distributions here is not normally distributed? Okay? Then basically, if you have a model with a distribution here, P of theta, all right? Then we have that the model will be LAN, locally asymptotic normality, at the true value theta, if basically the log likelihood ratio can be written here as a quadratic approximation, which related to the normal models we've seen on the previous slide, plus some rest here, right, that goes to 0, okay? Where basically this delta here is just a vector that converges to a normal distribution, all right? And I here is the information matrix of this guy here, okay? So what's nice with this LAN property, if a model is LAN, then basically we've got a nice and important implication, is that if you have a preliminary estimators, right, a preliminary estimator which is square root of n consistent, so you know that as sample goes to infinity, you will reach the true value, then basically if your model has the LAN property, you can obtain in one step, all right, an efficient estimator. So you start from this preliminary estimator, let's call it tilde tau, right here, tilde theta, sorry. You will do some correction here. This correction depends on the delta vector here, which I will define in a minute, and the information, the inverse of the information here, okay? So basically, we'll compute this delta terms and this information matrix terms at the value of the preliminary estimators. And this correction here, basically, will give you an estimator theta hat, which is asymptotically efficient. So in other words, this one-step correction will give you an estimator as efficient as the maximum likelihood estimator under the true distribution. All right? And so this delta here, which is the main, the most important terms, which is called the central sequence, is just basically the score factor. All right? And so what is it? It's just the first order derivative of the likelihood function with respect to the parameters. All right? So basically what we do, we start from the preliminary estimator and we'll correct it by just adding this term here, where this is the score function and the information matrix here, which is equal to the square of the score function. So once you've got the score function, basically you can compute, you can replace theta here by the value of the preliminary estimator. You compute the information matrix here and you replace it, you estimate it at the value of the preliminary estimator, and then you directly have your one-step estimator, okay? Your one-step efficient estimator. So even though you start from a really poor estimator in terms of efficiency, right? So like the two-stage least square estimator, which is really inefficient, but we know that is consistent, then basically here with this one-step estimator, you will directly get the efficient estimator. So an estimator which cannot be beaten, which can, the most precise estimator, it exists. All right? Is it clear? Any question up to now? No? Okay, great. So now that you've seen how the land property works, let's now apply it to this linear model with spillovers, this SAR model. So you remember what we're interested in is the model that accounts for spillovers between individuals. And here, what I will focus on is the model with endogenous effects, right? So you've got this spatial like here, where basically the outcome of an individual depends on the outcome of neighboring individuals, right? So in that model, what we do, we just consider the same assumption as the econometric paper by Lee with respect to the interaction matrix and the regressors. However, what we will do, we will relax this normality assumption of the distribution. So we won't assume that the error term here are normally distributed. Instead, we will just consider more general case of distributions. Okay? And however, we need to maintain IID. Okay, because it's a maximum likelihood framework. So basically, in these settings, we need to have this IID. We need to stay in this IID world. But later on, I will show you that we are currently working on expanding that the model to heteroscedasticity and clustering. Okay. So let's first look at the efficient parametric estimation. Okay. To do that, assume that F is known, so you know the distribution, and you know that it's parametric with some vector here, gamma, right? So gamma here represent the parameters of the distribution. So the likelihood function, the log likelihood function can be written that way here, where you've got here the Jacobian of the transformation, which appears just because you've got a simultaneous model, right? Observation I is linked to observation J through the endogenous effect, all right? And here you've got the sum of all individual densities, right? It's just because the error term are assumed to be ID. So we can write the likelihood function in terms of the density of the error term, yeah? But we can write it in a different way too. Okay, we know that the distribution of the error term can be characterized by the distribution function f, okay? Or similarly by the quantile function, okay? So in other words, basically, we know that the density is equal to the derivative of the CDF with respect to its argument, and the distribution, the CDF, is equal to the inverse of the quantile function. Okay, so you remember, quantile function, you start from a uniform distribution, so between 0 and 1, and you apply the quantile function to obtain the quantile, so the generated numbers from this distribution. So it's exactly the opposite, the inverse of the CDF. For the CDF, you start from the quantile and you end up with a uniform distribution. Okay, so basically, so you end up with numbers from distribution which is from uniform, which comes from a uniform distribution. All right. So basically, this means that the density here, F, can be written that way. All right. And you can tell me, but why is it useful? It's useful for cases where the density is not explicitly defined. So you cannot write the function for the density. However, you can nevertheless write the quantile function. So there are distributions. I will present you one later, like the 2K GNH, where the density is not explicitly defined, but the quantile distribution is explicitly defined. So we can write everything in terms of the quantile function. Okay? And so if we write the log likelihood in terms of the quantile function, we will have, oops, sorry, we'll write the likelihood function that way. Okay? So that's our likelihood function. What I would like to remind you is that basically, even though we write the likelihood function, we will not maximize it. Okay? What we are interested in is finding a one-step estimator. Why don't we maximize it? Just because sometimes it's not possible. For instance, when the density is not explicitly defined, or when you have a Laplace distribution where you cannot maximize the likelihood function. Okay? So what we do is we'll compute this one-step efficient estimator. Okay? Where delta here will be the normalized score function. Okay? And again, this information matrix can be computed as the square of this central sequence. So what this means is that basically we only need to compute the first order condition and we are mostly done. All right, so you impose a distribution. Okay, you write down the likelihood function, you compute the first order conditions and you are done. Okay? Only what you are only required to compute integrals to compute the information matrix. And so, as I told you, the central sequence is just the first order condition. So it's the derivative of the log likelihood with respect to each set of parameters, so the betas, the lambda, which represent the endogenous effect, right? Intensity of spillovers, and these gammas here, which correspond to the numbers of parameters of the distribution. For instance, if you have a Laplace distribution, it's a 2-parameter distribution, then gamma will be of size 2. However, we will see that for the 2K distribution, 2K GNH, we'll have a parameter with 4. We'll have a distribution with 4 parameters. So here you will have 4 derivatives to compute. Okay? So that's for the general picture. How does that work? I will then specify the estimator for 2 particular distributions. But currently, I just show you how it works, how it works in general terms. Basically, so the lab allows you to have a one-step efficient estimator. For this, you will just start from a preliminary estimator, which should be square root of n consistent, all right? And we just correct it, all right? So the main point you have is first you need to have a preliminary estimator. Here, what we do in this paper, what we propose to is just rely on two-stage least squares. All right. So what we do, we just first estimate the model by two-stage least squares. Why two-stage least square? Because it's really easy. Okay, it doesn't take it just you get it in a second. It's consistent and basically, yeah, it does not require any computation complexity, right? Once we have this two-stage least square estimator, we compute the residuals, right? The residuals is being y minus x times this beta tilde, okay, minus lambda tilde times this endogenous effect, okay? Just a small remark here is that in these residuals, we don't include the constant term. So basically, it's an uncentered error term. Why is it the case? It's just because here, the constant term is viewed as a nuisance parameter, okay? And so the constant term will be accounted for in the location parameter of the distribution. So what we do generally when we do a regressions basically, for instance, a linear regression, we just add a constant term to model and impose that the error term is centered around 0. Okay? Here, we just take a different route, but which leads to the same results, is that basically we don't impose a constant in the model, but basically we allow the location parameter of the distribution to be different from 0. And basically, this location parameter will represent the constant term of our model. Okay? So first we have a two-stage least square estimator, for lambda, for beta, and for lambda, all right, which allows us to compute these residuals. Now we also need a preliminary estimator for the parameter of the distribution, the gammas here, okay? And to do that, basically what we do, we use the quantile least squares developed by Xiu and co-authors in 2014. And what does it look like? It's just basically one type of least squares thing. Well, what we do, we will minimize the square distance between the residual quantile here and the corresponding theoretical quantile. See, that's a quantile function of the considered distribution. Okay, so we know that we impose that the error terms are from a distribution. Let's call it F. Okay, this distribution F has some quantile function. Let's call it Q. And basically, we will compute the exact value of this quantile function under this distribution, right? Which depends on the parameter gamma here. Okay, and so what we will try to do is to minimize the distance between the empirical quantile and the theoretical quantile. Okay. Once we've got this parameter gamma tilde, okay, the gamma tilde are the value of the parameter which minimize this distance here, then basically we have a preliminary estimators for all parameters, for beta, for lambda, and for gamma. And so from there, we can evaluate the central sequence and the information matrix at the preliminary estimator. Okay? Once we've done that, basically we can compute the one-step efficient estimator. Okay, you remember what we need to have? It's this delta tilde parameter, this preliminary estimator. Once we've got it, we compute the central sequence, evaluate it at this value, the information matrix evaluated at this value, and then we basically can compute this guy here, okay, to obtain this one-step efficient parameter. Okay? Okay, so a problem with that approach is that we impose a specific distribution. We just say, for instance, F, the density, is a student distribution. But what happens if F is misspecified? So this means that it doesn't correspond to the true distribution. In that case, generally, theta hat will be inconsistent. So it will not converge to the true value as the sample size increases. Okay? And to do that, and to solve this problem, basically we have two possibilities. One, the first one is to rely on a flexible parametric distribution. For instance, here, what we consider the 2K GNH or the Jones and Pusey SAS distributions, which allow to approximate well many parametric distributions. But of course, many other flexible distributions could be used. Here we just take these two ones because they allow to approximate many distribution ones. But if you think that they are still too restricted, you can consider generalized version of this, or even alternative distribution. That's the first solution. The second solution is to go to a semi-parametric solution. Semi-parametric, why does that mean? This means that one part of the model is parametric, that's the beta and lambda. You still need to estimate these two sets of parameters. However, the distribution is left non-parametric. So we don't assume any parametric distribution, okay? So in other words, we stay agnostic with respect to the distribution of the error term. And what we'll do, we will rely on the functions of the residuals which are invariant with respect to the underlying distribution. All right? So let's first look at this flexible distribution, flexible parametric distribution. The first one I will present you, so that's just really an example here. So it's the Tukey-GNH, which has been introduced by Tukey in 1977, which is basically a transformation of the normal distribution. So we start from a normal distribution, we hammer it on the left, on the right, and basically we will just transform it such that it can allow for asymmetry, all right, skewness, and also for heavy tails, right? So basically we transform the normal such that it can have heavier tail than the normal, but also be skewed, okay? How does that work? Now, if you have Z, which is a standardly normal distributed, random variable here, basically, we will transform this Z to obtain this X variable here. So X is a transform of Z, it's a transformation of Z, right? Which depends on 4 parameters. Xi, here, which will be the location parameter, which will represent the median here, not the mean. All right. Here you will have this sigma parameter, which will be the scale, so the dispersion of the distribution, plus this tau function here. And this tau will correspond to this function. All right. And basically this tau, these tau functions will be the Tukey-GNH transformation, where G here will account for the skewness of the distribution. So if G is equal to 0, you've got a symmetric distribution. While if G is positive, you will have skew to the left, a skew to the right, sorry. While if G is negative, you will have a skew to the left distribution. And H here, sorry again, H will represent tail elongation. So H cannot be negative, all right, and should be smaller than 0.25. Why 0.25? It's just because in this model, we basically need the 4th moment of the error to exist. And to guarantee the existence of the 4th moment, need H to be smaller than 0.25. All right? So let me just show you how this Tukey can be used to basically approximate different functions. You start here. Oops. Basically here, okay, it works. So when playing with the G parameters, you can see that you change the skewness of the distribution. Playing with the H will give you heavier tail. You can see that basically the tail are become much heavier than the normal. And basically you can combine both of them to basically approximate a large numbers of distributions. Okay? So it's quite a flexible, it's really a flexible distribution, this Tukey distribution. All right, so how does that Tukey works? How should we obtain the estimator under this Tukey distribution? Quite easy. Basically, you compute the preliminary estimators for beta and lambda using either 2-stage least squares, or you can also use QML or GMM approaches. In the second step, you compute the preliminary estimators of omega, of Xi, omega GNH, so the parameter of the distributions here, using the quantile least squares. In the third step, you compute the expression for delta and the information matrix, which are explicit, and depend on function of the quantile functions. I can show you the formulas if you're interested in it. And then we can obtain the efficient estimate. If you really wish to, you can refine this one step by performing it several times. Okay? I will show you an illustration later. The second flexible distribution we consider in this paper is the SAS distribution. This has been developed by Jones and Pusey in 2005. And basically, it's another transformation of the normal, which allows to model skewness, but also tail weight. To have, it basically can model distributions with tails lighter than the normal, like the beta distribution, but also tail heavier than the normal, like the student distribution. Okay, and it's called the hyperbolic sin, arc hyperbolic sin, so SAS here, distributions. And again, it's just a transformation of the normal distribution using this transformation over here, where basically epsilon here will control for the skewness. Okay, so a positive epsilon means a distribution skew to the right, while a negative epsilon will mean a distribution skew to the left. And the parameter delta here, positive, which controls for the heaviness of the tail. So if your parameter here, epsilon and if epsilon is equal to 0 and delta is equal to 1, you are under the normal distribution. Okay? If your delta is larger than 1, you have a distribution with lighter tail, with tail smaller than the normal. While if your delta is between 0 and 1, you will have a distribution with heavier tail. Okay? And the problem with this SAS distribution is that, okay, its density is explicit. However, it's really hard to estimate it by maximum likelihood just because there is some numerical convergence issue. And here with the estimator we propose, we don't need to maximize the likelihood function. We just need to compute a one-step estimator. Okay, so how does that start? Here, basically for the SAS errors, here you can see that the epsilon is equal to 0 and d is equal to 1, which is the normal distributions. And so basically when we start to when we start to change it, all right, so we change epsilon to be positive or negative, then we'll see that it will change the skewness. All right. And basically here you can see that if d is larger than 1, the tails become lighter than the normal, while for d smaller than 1, you can have heavy tails. And you can play, of course, with both of them to have really weird parametric distribution, such that way. You can see that basically the SAS is able to approximate such type of distribution, which is quite weird because here you can see that there's a bump over there, while normally the distributions are just more, the bump is on the other side. Okay? So, oops. How do we implement that? It's exactly the same for the SAS distribution as for the 2K GNH, all right? And the last thing I would like to say about this flexible parameter, this flexible distribution, is that if this SAS or 2K approximate well the underlying distribution that you don't know, okay, then basically the obtained estimator will be very close to the efficient one. Okay, so they will be efficient if the underlying distribution is a SAS or a 2K, but if this SAS or 2K approximates well the true underlying distribution, then basically your estimator will be close to the efficient one. Okay? How do we know whether the SAS or the 2K can approximate well a distribution? Look at this case here. The true distribution is a chi-square, it's a chi-square tree distribution, and let's see how we can approximate that distribution using first the SAS and then the 2K. So the SAS here is in red. Okay, so we will play with the different parameters. So it's slightly asymmetric to the skew to the right. Then basically what we do, we change the tail elongation, we change the location parameter, and here with the omega, we just change the scale parameter. And you can see that basically we observe that the SAS already does a good job of approximating the chi-square distribution. We can do exactly the same for the 2K, where here, what we'll do, we will just basically change the location parameter, and basically then we will change the scale of the distribution, and you can see that by doing that, we will come to a point where the 2K does a really good job in approximating this chi-square distribution too. Okay, so you can see that they are really flexible distributions. So that was the first solution if you suspect F to be misspecified. All right. The second solution is to go to the semi-parametric world. Okay, how does that work? Basically, what we'll do, we will weaken the assumption of the distribution. We just say that F is part of a family of distribution, call it F naught here, where this F naught is composed of all strongly unimodal distributions. All we ask for F is to be strongly unimodal and of median 0. Okay? Under this set of distribution, basically, we will be able to define a semi-parametric efficient estimator. How does that work? Basically, it occurs in 3 steps. First, assume F is known. Okay? So you will write the likelihood function under this F distribution. Okay? It looks really like the parametric word. Okay, so assume that F is known. Okay, as F enjoy the land property, just because we impose its differentiable nearly everywhere, which is really weak assumption. Basically, we can write the central sequence or the score function for beta and for lambda, which take that form. All right, I mean, if F is the normal distribution, you will really easily find the form for the central sequence. Here, it's just a bit weird because you've got this phi here, which is basically minus F prime over F, because we write it for a general density function F. Okay? So here we assume first that F is known. However, we know that if F is misspecified, then theta hat, so based on this F, is generally not consistent. What do we do? In a semi-parametric world, we'll basically use a transformation of the error term in the construction of the central sequence. So instead of relying on the error term, we'll rely on the transformation of the error term. Okay? And this transformation will be the ranks and the sign. Why? Because this transformation, these ranks and sign, are not affected by the true distribution. Okay? So for all F, for all distribution belonging to this family of unimodal distribution, basically the ranks and the sign will always be the same. Okay? And these ranks and sign is what we call a maximum invariant. This means that it's the best transformation can have. Best in the sense that this transformation will yield the semi-parametric efficient estimate. Okay? And so in other words, how do we go from the parametric to the semi-parametric solutions? We will just condition the parametric central sequences with respect to the signs and the ranks. Okay? And so we'll obtain this delta tilde central sequence, which is a semi-parametric central sequence. Okay, and it will be valid. So this means that this central sequence will lead a consistent estimator here for any distributions in F naught. All right, so whatever the distributions, we know that this central sequence will lead to a consistent estimator. However, we don't want an estimator, we don't want the estimator to be semi-parametrically efficient under a given distribution. What we would like to have is a semi-parametric efficient estimator for any distribution. So basically an estimator which does not depend on the distribution F. And to do that, basically what we'll do, we'll just replace the density F by an estimator. So we'll estimate F using a kernel estimation. So instead of working with a true F, we'll just estimate it. All right? And we'll just obtain a one-step semi-parametrically efficient estimator theta hat star. Yeah. We start again from this non-parametric, from this initial estimator here, and that we will transform. Okay? So I'm done with the econometrics. Okay, now I will just show you. I will just show you how it works on finite data, on finite sample. To do that, we just do a quite simple simulation setup. We've got a SAR model with a constant term here and explanatory variable X. We just use 3 sample size, even though here I will only present the smallest one. So we do 1,000 replications. For W, we consider 10 nearest neighbors. And basically, yeah, all the estimators we will propose here, the 3 estimator, the one based on 2K, the one based on SAS, and the one based on rank and sign, are all use 2-stage least squares as initial estimator. And basically, we will measure two things, the bias and the variability. The bias will be measured as the difference between the true value and the median value of the estimator. Okay, and we will have a dispersion which will be viewed as the interquartile range of the estimator divided by 1.349. Okay, so we consider different distributions here. Okay, so we'll consider 10 distribution, the normal one, also light tail data, and really skewed distributions here, like this one. The gamma, the chi-squared, the log normal. We also consider the 2K and a SIS. Okay? What do we have here? Basically, what I will report here, I don't spend too much time on this Monte Carlo simulations. Basically, here I report the dispersion of lambda, right? The interquartile range. Under normal distribution, you don't see anything, right? So what I report here, I just compare the QML estimator of Lille, the GMM estimator, and the three estimator we propose, the right-hand side. So this means the semi-parametric estimator, the one based on the 2K GNH in yellow, and the one in purple, the one based on the SAS distribution. And what's remarkable here is that under normal distribution, you don't see any difference. So all estimators are comparable to each other. However, as soon as you leave the normal board, basically you can see that the QML in blue and GMM in pink are much less efficient than the three others. All right, for instance, here you can always see in all pictures that basically there are two groups: the classical estimators used in the literature, like the GMM and the QML, and here below you have this three estimators that we propose here, three efficient estimators. So the non-parametric, the one based on the 2K, and the one based on the SAS, sorry, the SAS distribution. Okay. Here I do the same for beta one, so the coefficient associated to x, where basically you have exactly the same. You have exactly the same pictures, where you have always, I mean, most of the time, not always. You will have that the QML and the GMM are the least efficient, and you have a group of three here, or here, or here, which are much more efficient. All right? Corresponding to the bias, you can see that all five estimators here are completely unbiased. You can see that there are some change in the pictures, but look at the scale here, it's really close to zero. And besides, this bias really diminishes as the sample size increases. Okay, so what I will maybe finish this presentation is is to apply this estimator on real data. And for this, we took the paper by Beren, Sertur, and Kalk. It's a Journal of Applied Econometrics paper, where they estimate a trade model using spatial econometrics methods, basically to assess the effect of a Canada-US border on trade flows. So they look whether having two regions on each side of the border will have a negative effect on the trade flows. And so the model they estimate is this one, where they want to estimate, they want to explain the manufacturing export from region I to region J, based on the distance between these two regions, the log of the wage in region I, in the exporting regions, the demi-heat that presents the border effect. And here, this guy here represents the effect of other regions' export to J on the export of I to J. All right, so this means that the export from I to J depends on the export of other regions to J. All right, and the interaction scheme here is made of the basically of the relative share of the relative population share of region K in the sample size. All right. So basically, that's the interaction matrix they use, which is based on economic theory, basically. And the objective here is just to compare what the authors found using normality assumption to what we obtain when we relax these normality assumptions. Okay, what they obtain in the paper is these results. Okay, where the lambda is the spillover effect, and you can see that basically it's not significant, where t stat is equal to 1. Okay, so basically in their model there is no spillover effect. Okay, here what I reproduce is the QQ plot of the error term, and you can clearly see that basically the error term is really different from the normal distribution. So this means there is huge room for improvement. And so what we will do, we will just try to relax distribution effect by estimating the model by two-stage least squares and by GMM. And you can see that basically for all these cases, you still don't find much different result because you are still really far from significant results. However, when we rely on this three estimators that we propose, the one based on the TK, the one based on the SAS, or the non-parametric one, you can clearly see that basically you have two effects. One is a sharp decrease in the standard errors. Okay, you go from nearly 0.03 to 0.02. Okay, so that's nearly a 50% decrease. All right, and this is valid for all standard errors. Compare this, for instance, to this. Yeah. Okay. Or for all variables, you have a strong increase in the standard error. So this means a huge increase in precision. And also you have also a change in the point estimate, where the lambda goes from 0.03 to 0.09. So this means a 3 times increase in the point estimate. And these joint results means that now we observe significant spillovers. All right. So this means that relaxing the normality, so looking for more efficient estimator, can really change your qualitatively change your empirical results. And so we found that was quite important to have this. Okay, and we finally, what I will finally represent here, in the histogram, you've got the histogram of the residuals. In dark, in black here, you've got the normal approximation to this. And basically in blue here represent the estimated density of the residuals, which is used for the non-parametric case. So you can see that basically our distribution is a much better approximation of the error terms than the normal distribution. So just to conclude, what we do here, we propose two estimators based on local asymptotic normality to achieve efficiency. These estimators can be viewed as maximum likelihood estimators, all right? So this means that you cannot basically beat them, all right? Last 3 points is that even though I present these estimators for the SAR model, they can also be used for classical linear models. We just need to simplify them, all right? So for any linear model, you can use these estimators. And basically, yeah, last point is that what we are currently working on is just to consider heteroscedasticity or clustering, but it's not that easy because maximum likelihood estimator for the SAR model is inconsistent as soon as we try to introduce heteroscedasticity, so we need to work on that. So thanks a lot for your attention. I hope it was clear. And if you have questions, comments, I'm all yours.
Thank you so much, Nicolas, for that very interesting presentation.